Okay, yeah, let's just go straight on. We're looking at FM1, still looking at 9A. It's the second video, and we'll go straight in for example 3. So I'm given the vector equation of my line. Now they're using t, whatever, 1 minus 6 minus 2. Given that the point AB0 lies on L, find the values of A and the values of B. Well, they give me an actual point, AB0. So I've got 3 equations. I'm going to use the bottom equation to find T, and then I can use that value of T to find A and B. So 5 minus 2T equals 0. So T equals minus 5 over 2. Then 3 plus T equals A. So A must be a half. And 2 minus 6T equals B. So B must be 17. Straightforward enough, nothing really to say about that. Example 4. Now give me a vector equation of the line 2, 5 minus 3 plus lambda 6 minus 2, 4. Show that another vector equation is 8, 3, 1. So really they're saying show that this position is on this line. 3 minus 1, 2. Well, first of all, look at the direction parts. We can see straight away that they're parallel because 6 minus 2, 4 is double 3 minus 1, 2. So we can say that parallel since 6 minus 2, 4 is 2 lots of 3 minus 1, 2. So if we can prove that this point is on the line, then we can say they're the same line. 8, 3, 1 equals 2, 5 minus 3 plus lambda 6 minus 2, 4. What I want to do is look at each of the 3 equations, solve for lambda, and show that lambda is the same for all of them. 8 equals 2 plus 6 lambda. Lambda is 1. 3 equals 5 minus 2 lambda. Lambda, fortunately, is 1. 1 equals minus 3 plus lambda. I forgot I was doing a video. My handwriting's got really small, isn't it? Minus 3 plus 4 lambda, sorry. Lambda equals 1. Therefore, 8, 3, 1 is on the line. So an alternate form, R equals 8, 3, 1 plus, and I'm using mu because I don't want to use lambda. It must be a different multiple because I'm starting at a different point and using a different direction. Done and done. Straightforward enough, I think. Example 5. Okay, example 5. Turning my vector form into a Cartesian form. So I'm given A1, A2, A3, the general form of the vector equation of a line. Now remember, this point actually is my x, y, z coordinates. So x equals a1 plus lambda b1. Y equals a2 plus lambda b2. Z equals a3 plus lambda b3. I can rearrange this to make lambda the subject, x minus a1 over b1. I'm going to make lambda the subject here. Y minus a2 over b2, and make lambda the subject for my third equation, z minus a3 over b3. So because all these expressions are equal to lambda, they must be equal to each other. Oops, I took it the wrong way. Now, I don't need to write this last bit, but I'm going to. We're given this. You don't need to remember this. We're given this. This is a Cartesian equation. It's not necessarily in a form that we're used to, but a Cartesian equation just means an equation in x, y, and z. And this is an equation in x, y, and z. This tells us the relationship between the x, y, and z components, the x, y, and z ordinates at each point on the line. So this is like my y equals mx plus c, but in a different form. Part B then, just sub into this. So that was part A. Part B, I'm given 4, 3, minus 2 plus lambda minus 125. So just write this in Cartesian form. Well, close enough. I mean, easy enough, sorry. Done. And I'm just going to leave that minus 1 down there. Okay. Oh yeah, no, there is another one. Example 6. Hold on, let's pause a second and have a read of it. Okay, so example 6. This one's thinking about. I've got a line. Minus 2, 1, 4 plus lambda 1 minus 2, 1. And I want to show that position P is not on the line. So what I'm going to show is if I set them equal, for the x coordinate to be equal to that has a particular value of lambda, for the y coordinate to be equal to the middle row, solve for lambda, for the z coordinate to be equal to the bottom row, solve for lambda. If the point is not on the line, I will not have three different values. I will not have three equal values for lambda. I'll have, well, three different values for lambda. So I'm going to solve each equation. I'm going to pause the video till the dog stops making noise. No, she hasn't stopped making noise, but I'm going to carry on anyway. She's clawing the carpet if you're interested. Right. So I solved each of the three equations, made a bit of a mistake there and put curly brackets in where I shouldn't have done, but you can see that the values of lambda are different, therefore P is not on the line. So the first part is straightforward. The second part is going to blow our mind. I've got a circle with P at the centre, and I know the position of P. It's 2, 1, 3. My line goes through A and B, and we're told that A has a position 0, minus 3, 6. Find B. So what I'm going to do is this. I'm going to find the distance between the two. That's Pythagoras. Because I know that there is a radius here, AP and BP are both radii. If I find that distance, then I know that distance. I can get an expression for point B in terms of lambda. I know how far away it is, so I can get an expression for the length BP, and I should be able to come up with an equation. Right, so first things first. The vector AP, well, how do I get from 0 to 2? I add 2. How do I get from minus 3 to 1? I add 4. And how do I get from 6 to 3? I take away 3. That's the vector AP. The length AP, it's just Pythagoras in 3D. I haven't explicitly said this before, but it works in 3D just as it does in 2D. square, 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 add together, take the square root, done. So I know that the distance BP is root 29. Therefore, BP is root 29. Now B is on the line. In the book, they use that position. I'm going to use position A. It doesn't matter, of course, because A is also on the line. So 0, minus 3, 6, plus lambda, the direction part, 1, minus 2, 1. So my value of lambda is going to be different to the book's value of lambda because they've used a different starting position to come up with an expression for B, but that's okay. And it's convenient for this question to write this as a single vector. Okay, so that's the position of B. It's the position of A plus lambda times the direction part. And we're going to find out what lambda is, which means we're going to find out the position of B. So how do I get from B to P? Well, how do I get from lambda to 2? I take away my lambda and I add 2. How do I get from minus 3 minus 2 lambda to 1? I add on 4 and I add on 2 lambda. How do I get from 6 plus lambda to 3? I take away 3 and I take away lambda. Okay, right, so that's the vector BP. I know that the length of this vector is root 29, so I can write that. Root 29 is the square root of, I'm going to write minus lambda plus 2 is 2 minus lambda. It's just easier in my head to square that. Plus 4 plus 2 lambda squared plus minus 3 minus lambda squared. I'll simplify this. I'll use magic to speed it up. There you go, magic. Expanded, squared both sides, simplified, simplified. I'm going to solve. Now, what I've said is the point on the line, which is root 29 away from P, has this expression. So that's why I've got two values for lambda. Now clearly lambda being 0 will give me point A. So lambda equals 0, which is not what I want. Lambda equals minus 3. That should give me point B. And if lambda equals minus 3, let's sub it into the expression I got for position B. B is 0, minus 3, 6, plus minus 3 times 1, minus 2, 1, which is 0 minus 3, that's minus 3. Minus 3 plus 6, that's 3. And 6 minus 3 is 3. Let me just check that that's what they got in the book. It is what they got in the book, so we are done. It's a big, horrible question, and you might want to rewind and get your head around it. Have a go at 9A. This may well take us 2 lessons. There's quite a lot of questions, and there's a lot of thinking to be done. We'll have a chat about it in the lesson, see if we need to take 2 lessons or not. Okay, enjoy.